All right, so this is acid-base disorders, part 2, because we kind of went over it in the first part of class in Unit 1. But this focuses more on the kidneys, and she made it pretty confusing today, so the purpose of the video here is just to clear up the confusion and get rid of the graphs, because graphs always confuse everybody. I don't know why any teacher would include them in their presentation or in their lecturing. So we need to describe two processes, okay? So we either got an observation of the body. We either can have the body be within a normal pH, which is about 7.35 to 7.45, or we can have it be acidotic, which would be anything under 7.3.5, or more alkaline, which is anything over 7.45. Now, our body works best in a range, that range of 7.35 to 7.45. If we get outside of that, on either side, we run into problems and our proteins don't work very well. Our whole body goes to shit. So, and anything under like 6.9 or 6.8 pH, you're gonna die. So there's my little cool factoid for this video. All right, so how do we classify the disorders? Okay, so we classify them based on one, whether they're making the pH go up or down, so whether they're an acidosis, which is the pH is going down, or an increase in hydrogen protons, or we classify them as an alkalosis, which is an increase in pH, or a decrease in hydrogen protons, okay? And within that, we've got specific sets that describe them as to what's driving the process. So what's the problem? What's causing this pathophysiological condition and making our body either acidotic or alkaline. All right, so there can be two main ways that either of these processes can happen. It can either be driven by metabolism, so metabolic, or it can be driven by the respiratory system, so respiratory. All right, and I've listed off some of the common causes of each one of these processes just to get a better understanding of how they work. So the one I always like to start with is a metabolic acidosis. And the way I always think about metabolic acidosis is I think about DKA, or diabetic ketoacidosis. So when you're going to DKA, you're producing a bunch of ketones. That puts your blood pH way down low. It's a very common medical emergency. We saw people in the ER with it all the time. You can get really low, happens with type 1 diabetes. So when that happens, what's driving the pH down? Well, it's because we have a pathophysiological condition where we can't get glucose into the cell, and our metabolism is compensating for that by producing ketones that our body can run off of. So we classify that as a metabolic acidosis. And there's also other things. So pretty much anything with the metabolism or that has metabolism as a driving factor is going to be something that's not associated with the pulmonary system. Okay, so nothing with the lungs is going to be classified as a metabolic acidosis versus alkalosis. How do you interpret whether something is a metabolic acidosis? Well, the first thing you should know right away is if you see a pH below 7.35, below that, you should know that the process is an acidosis. So we can narrow down, okay, in our problem or our figurative test question that it's not going to be an alkalosis. We can cross those two out. These are our four options of what the process could be if we're dealing with a question like this. Now, we need to distinguish between a respiratory acidosis and metabolic acidosis. So one way we could do that is look at the clinical signs and symptoms, like what's happening to them, what are they displaying as, or we can look at our laboratory tests. So our laboratory tests mainly are going to come in the form of blood gases and comprehensive metabolic panel, but the main two we look at is our partial pressure of CO2 and our concentration of bicarbonate ion. So if we remember back into that first section, we know that bicarbonate is the main way the body is going to buffer against acid, okay? So if you think that our pH is going to be decreased, you would expect that the body would increase the amount of bicarbonate, excuse me, the word escaped me. Okay, and you would be right for a little while, but eventually that's going to fail and your body's not going to be able to cope with that. And if, in this case, we might also be running into a renal failure where your kidneys are failing and they're unable to synthesize new bicarbonate ion, okay? So the highest yield and the best thing I can think of to make this stuff as simple as possible is this. Look at this table right here. Is the pH going up or down? We know that it's an alkalosis if it's going up. We know if it's an acidosis if it's going down. Boom, done. All right? Now, the fastest way to tell between if it's a metabolic or a respiratory driven pathology is to look at where the mechanisms are, or where the levels are going. If the levels of pH or PCO2 and HCO3, so bicarbonate, are both going in the same direction, they are going to be a metabolic process. This makes it as easy as possible. Look at this, metabolic alkalosis. We're going to have an increase in PCO2 and an increase in bicarbonate ion. The arrows are going the same way. The levels of bicarbonate and the levels of CO2 are going to raise, okay? And I'll explain this more in detail on like the mechanisms for this, but just so we can get like the highest yield information right now, I'm just explaining this first off. All right, so we also know that if these are going the same way, then we know that a respiratory acidosis, our PCO2 and our bicarbonate are going to move the opposite ways, okay? And depending on which way, which one goes, we're going to have an acidosis or an alkalosis, okay? So, which would you expect to increase if you were having an acidosis in respiratory, or a respiratory acidosis? Well, we would expect us, since all the CO2 is our major driver of acid in our body for the respiratory system, that we would have an increase in CO2. So we can't get rid of it. So we have our partial pressure of CO2 increase, and that is going to increase the amount of hydrogen ions in the blood because carbonic acid is formed. So our bicarbonate ion is going to decrease because that is being used up in our buffer system to buffer out the problem, or to buffer out this acidosis, all right? Now, our respiratory alkalosis. So our respiratory alkalosis is going to be the same thing. It's going to be moving in opposite directions. One's going to be moving down, one's going to be moving up. Always look at the PCO2, always look at the bicarbonate ion. Quick and easy, high yield. Opposite directions, okay? PCO2 is going down, so this could happen in hyperventilation, congestive heart failure, or anemia. I'm not going to read off the entire table because I put it up here and wrote it up here so that you guys can read it all for yourselves because it's fairly straightforward. We're going to decrease the amount of CO2 we have in our blood, and that's going to make us alkaline, or more basic, all right? And we're going to increase the amount of bicarbonate ion, all right? And that's going to make us even more alkaline, all right? Because we don't have as much Hc3O or bicarbonate being used up to buffer hydrogen protons, because not enough is being produced by the CO2 in our bloodstream. We don't have enough CO2 to make an acid bloodstream, okay? All right, so some of the common things for this. I think this is high yield to know too, because if you know some of the common ones, they're probably going to be used in the questions, and if you know which one is responsible for which process, you already know it. You don't even have to go through this, okay? So metabolic acidosis is I wrote it as the beatus, like Willard, that guy from those commercials, you know, diabetes. And then we've also got Addison's disease, renal failure, common one, and a general increase in acid production. So you could also have a salicylate overdose, like an aspirin overdose. If you take a bunch of that, you'll get the body really acidotic. Renal failure, obviously you're not going to be able to, the kidneys aren't going to work as well, so you're not going to be able to synthesize the bicarbonate you need to buffer your acid state of your blood, and your pH is going to tank because of that, so it's going to lower. So the way that we compensate for a respiratory, or a metabolic rather, acidosis is we increase ventilation, so that decreases our CO2. And a decrease in CO2 means a decrease in carbonic acid, and thus a drop in blood pH. And this only, works to a point, so fair warning. Metabolic alkalosis. So vomiting antacids, not very common, not very high yield to know, but vomiting, we decrease the amount of acid we have in our stomach, which is our major source of acid in our entire body. Antacids, they neutralize acid, so that's also going to decrease the amount of acid in our body, etc. What's the compensatory mechanism? We're going to decrease our ventilation and retain CO2, okay? Easy enough. Increase CO2, increase amount of hydrogen protons in the blood, decrease pH. All right. Respiratory acidosis. These ones are compensated by the kidney, so I feel like these ones are a little bit higher yield to know. All right, so how do we compensate for a respiratory acidosis? So we're retaining CO2, and our bicarb is decreasing. Why is it decreasing? Well, because our bicarbonate is being used up to buffer that change in acid, okay? And the more that it gets combined with acid, it makes H2CO3, the less of it we have in our bloodstream, okay? So, to compensate for that, we're going to have to make more bicarbonate ion. So, the way we can do that is we can do that in the distal collecting duct and the distal convoluted tubule in the collecting duct. We're going to make HCO3 with the help of our glutamate, which is undergoing a complex series of reactions that I don't think are good to know. But they're going to make NH3. So NH3 is going to be combined with a hydrogen proton from the tubule, because we know that hydrogen protons are very freely filtered in the nephron or in the glomerulus. There's a bunch of them in there. If we take an NH3 from one of the cells lining the tubule, we combine it with this and water and CO2, we can also make we can undergo a complex series of reactions and make NH4 and then bicarbonate. Okay, so NH4 is a good buffer for urine because going back to the bigger picture here, we have to make sure that our urine's not too acidic too. So I was going to go through this. All right, and so we can increase the amount of bicarbonate we make, given that we're going to use this system of ammonia and also our phosphate system. So that's what she was going into today. We can combine phosphate to make H2PO4 minus and then undergo some more complex reactions with CO2. And this is also going to result in a net gain of bicarbonate. Okay? So the two ways we make bicarbonate, through that NH3 and through the PO4 minus systems of buffering in the kidney nephron. Okay? Easy enough. All right, so our respiratory acidosis, we're going to increase our reabsorption, and we're going to increase the amount of HCO3 we make. And then we're going to secrete more hydrogen protons, okay? So I'm gonna let you guys read through this. So I don't think it's as high yield to know, or I didn't think that's what people were having trouble with. Comment if I'm wrong, or put it in the group chat if I'm wrong, then I can make another video about how this all happens in the kidney. But I'm just making a video about like how to classify each one and how to solve these problems. All right. And then our compensatory mechanism for respiratory alkalosis, we're going to inhibit this system, okay? We're gonna inhibit the ammonium and phosphate buffer system, and that is going to decrease our reabsorption of bicarbonate, and it's also going to stop us from making new bicarbonate, and it's going to make us retain hydrogen ions, okay? So retaining hydrogen ions is one of the main ways that we can reverse or protect against, compensate for a respiratory alkalosis. All right, so in the nephron, this is kind of just the major steps that I want to touch on. Reabsorption of bicarbonate happens in the proximal convoluted tubule and the ascending loop of Henle and the early distal convoluted tubule. And those parts also secrete hydrogen ions. They do it in an exchange, so they exchange bicarbonate for hydrogen ions, and they reabsorb sodium secondary to bicarbonate. All right, or secondary to hydrogen ions, excuse me. Our distal convoluted tubule and collecting duct also reabsorb bicarbonate ion. Hydrogen is excreted, and K plus or potassium is absorbed secondary to hydrogen excretion. Also here there can be reabsorption of K plus. So in our distal convoluted tubule, if we need to retain H plus, this is where we're going to compensate for our respiratory alkalosis. So in the distal convoluted tubule, that's where we retain our hydrogen ions. In our respiratory acidosis, where are we going to secrete our hydrogen protons from? From our proximal convoluted tubule, our ascending loop of Henle, and our early distal convoluted tubule. All right, so I hope that kind of clears up some of the kind of major confusion about that. Remember, if there's one thing you need to change from this, or one thing you need to know, it's that CO2 and bicarbonate in a metabolic process are going to go the same way. They're both going to decrease or increase depending on whether it's an alkalosis or acidosis. And then a respiratory acidosis versus respiratory alkalosis, they're going to be going the opposite way. So the PCO2 and bicarbonate are going to be going opposite ways depending on whether it's an alkalosis or an acidosis. Highest yield thing to know, compensatory mechanisms, and then how it all happens in the kidney. All right? Hope that helps.